Hey everybody. So we're getting into our first hypothesis test. This is the simplest test that we have. And it's based on the old bell curve. Okay, so originally we would use a z-test, and we knew how to work with the actual bell curve, the original bell curve, and we could do a statistical test with that. But it turns out that there were a couple of problems with the original z-test. It was brittle and not robust. What does that mean? A statistics that is robust means that it will retain its accuracy even when its assumptions are violated a little bit or to a point. And we'll talk about those assumptions and what they are. But again, robust means it's resistant to problems. Brittle means that it breaks easily, that small violations of the assumptions can erode your accuracy, right? So robust means it will retain accuracy even in adverse circumstances. Okay? Um, and the other problem was the z-test required large sample sizes. And the t-test can still survive in a situation with small sample sizes. All right, so basically now the z-test is never used in modern statistics. In most cases, the t-test is preferred and will be more accurate. At any place where it would still be appropriate to use the z-test, the z-test, the t-test will match. So we almost never use the z-test anymore, and instead we use the t-test. And the assumptions of the t-test, and this is true for several other tests, these are the common assumptions for statistical tests like linear regression, ANOVA, the t-tests, right? So what are they? Normality, independence, and homogeneity, the variances. Okay, so let's start with independence. Why? Because we can't check it. It's not a statistical idea. Independence means that the data points in the sample data are independent of each other. That way, let's say they were taking a math test, and that was part of the research. The research data is scores on a math test. Independence means they didn't cheat off of each other, right? That the answers that they give, the scores that they got, are independent of the other research subjects. So there's no statistical test for that. Independence is just a research idea, and the protocols that the researchers use have to be done correctly, right? So we're not going to check that statistically. Homogeneity, the variances. What does this mean? Well, you've got to remember that variance, the square root of the variance is the standard deviation, right? So what we're saying is that if there are two or more groups, two or more samples, that they're drawn from populations that have the same standard deviation. Okay, that was a requirement of the traditional t-test. We have a version that does not require that, which, by the way, are defaults to. We don't have to change a setting, but it turns out that this isn't needed that much. And there is a Levene's test that checks for whether or not the variances are similar and whether we can use a pooled variance. Excuse me, the same variance. But there are some problems with the Levene's test. It erodes the power of the overall statistical inquiry. So we don't check that. It's not that we ignore it completely, but it's really at the bottom of the list. Right, so what we're checking is normality. What is the normality assumption? The normality assumption says that we have some evidence that leads us to believe that these data we're looking at were drawn from a normal distribution. That means bell-shaped. Okay? Again, the density plots that we look at won't necessarily be perfectly bell-shaped, but they'll have some evidence, right, that they were drawn from a bell-shaped distribution. And that needs to be ironclad. Also, we do have a problem with the small sample size. Small sample sizes, why? Because the homogeneity, the variance can be a problem with small sample sizes. Outliers can contribute to a problem with small sample sizes. Okay, so the data checks for the t-test. What are we going to do? We're going to look at a density plot and a box plot. Density plot, evidence of a bell shape, right? Box plot, we're looking for no outliers, sort of. That's sort of what we're looking for. Okay, so for the outliers, we have different levels at which we check. because T is robust, at a certain point, we'll proceed even with outliers. Now, let me put a caveat there. Not any outliers. It can't be completely riddled with outliers and very extreme outliers. That will still cause problems even for sample sizes of 40 or greater. But generally speaking, with just moderate outliers, for sample sizes above 40, the t-test is so robust that it's going to retain its accuracy, even though we violated that assumption a little bit. Again, we're not going to let it go to the extreme. Okay. In this sample size between 15 and 39, do not proceed with outliers. Okay, why? Well, outliers are influential data points, and they also influence the mean, and the mean is part of how we're calculating t. So these outliers can disrupt the accuracy. And so generally speaking, less than 40. And some people are less conservative. 40 is a pretty conservative number. Some people will say anything above 30 or 35 is fine. 40 is pretty conservative, but again, we all understand that proceeding with outliers is a problem in a small sample size, okay? But what about these tiny sample sizes of 14 or less? Well, then we're going to have to see a nearly perfect bell shape in the density plot, or we might use a stem plot, and no outliers. Everything's going to have to be nearly perfect. Why? Well, because it's just such a tiny sample size that we're going to need things to work out really well for us before those data are going to be appropriate for T procedures. Okay, so let's look at example 1, aggressive humor. So we know that the undergraduate population has a normal distribution for aggressive humor with an average of 29 and a standard deviation of 8, okay? So what is aggressive humor? Well, it includes sarcasm and put-downs. Also, you'll find if you investigate this, and by the way, you can just look up Wikipedia Humor Styles Questionnaire, and it will go over the actual instrument we used, which was the Humor Styles Questionnaire, and it will give you more details about this. But what we do know is that younger people use aggressive humor more often, and biological males use more aggressive humor than biological females. Okay, so what are we doing? In our personality data frame, we're going to test, and it gives us the significance level of alpha equals 0.05. That is the traditional. The standard alpha is 0.05. And we're going to test whether the aggressive humor scores are higher for these young male students who are 19 years old or younger. Okay, so this makes sense. We're going to have, sorry, let me get rid of the marks. We have the hypothesis, okay? And let's just quickly go over this. The null hypothesis, H sub 0, is that the average is 29. What average? The average of these male students who are 19 years old or younger, right? We're collecting data on these folks, and we're testing to see whether or not the average is equal to 29. Why do we use 29 in our null hypothesis? Because that's the average at UNG. These are UNG students. So we use the UNG average as our baseline assumption. That's our null hypothesis. The alternative hypothesis, the research hypothesis, hey, we think because younger people use more aggressive humor and males use more aggressive humor, that young males will use more aggressive humor at UNG. Okay, so mu is greater than 29, and I'm sorry, this is a copy-paste error. H sub A is what I was trying to put here for alternative. H with a subscript A for alternative hypothesis. And sorry that notation is messed up there. Okay, and I just explained what it was in words. The null hypothesis is that the average is 29 for these young males, and the alternative is the average is higher than 29. Okay, so what's going on here with the t-test? Okay, so what are we going to do? We are going to calculate t. And you'll find out I didn't get that number exactly right, but it's nearly 1.85. That's t, right? This 0 point is the average of 29. Okay, right? So we basically have this bell curve representing what? The UNG population, or at least our best estimate of the UNG population. What do we have? This blue vertical line is the test statistic that we calculate, and notice this area shaded, the area to the right. What is a p-value? The p-value represents the probability that results as extreme as the ones we saw, which are right here, or more extreme than that occurred. What's the probability if this is the correct, right? If this is the correct mean, that we saw results like we had in our sample, or more extreme. Okay, that's what the p-value tells us, and that's what this graphic is trying to show, that we're going to calculate this value, right? And using either a computer or a table, we're going to find the p-value, which is the percentage of area under the curve that's shaded here. The percentage of the area under the curve that's to the right. Why to the right? Because our null hypothesis, our alternative hypothesis used a greater than, right? If our alternative hypothesis used a less than, we would be shading over here. And there's even a not equal to where we're shading on both sides, okay? But in this case, we're shading above. Why? We're checking to see all the places where the results would be as extreme or more extreme as the ones we're seeing. Okay, so that's what's going on. Let's see if we can do that. Now, I'm going to switch to the notebook in a second. At the moment, I'll just say, hey, the data checks work out. So we end up determining that these data are appropriate for T procedures, and we'll move on. Okay, so what's going on here? By the way, I have links here, both in our course notes, and I have a formula sheet on my web page, and we use the t-table. I'm sorry, that's later when we look up. We'll look this value up in the t-table, sorry. How do I calculate the t statistic? I find it on my formula sheet, and it is x bar minus mu sub 0. What's the mu sub 0? Mu sub 0 is the average of 29 from the UNG overall population. Okay, so I calculate x bar from the sample statistics, right? I calculate S from the sample statistics, and I calculate N from the sample statistics. Okay, and you'll see, again, when we do the work in the notebook, you'll see all these values, right? The average aggressive humor score for these young males was 32.25. The standard deviation for our sample was 6.06. There were 12 young men in our sample, right? And as we do the math, we get a 1.85781. Okay? So that's how I calculate T. Now I know T, what do I do with it? Okay, so we have a formula sheet, and we're looking at the t-table, right? And what I want to do is I'm looking up this value in the t-table. Now I need to know a couple of things. Notice that it has df over here, and also notice the significance, right? So the significance of alpha equals 0.05, that means I'm going to be looking in this column right here. Sorry, my drawing is a little a little loopy. But I'm looking in the 0.05 column. Why? Because if you look back at the question, it said test at the 0.05 level of significance. If they said 0.01, I'd be over here, or 0.1, you can see these other places, right? Now, what's this degrees of freedom? It turns out that the degrees of freedom is n minus 1, sample size minus 1. Okay, and we'll find out that there were 12 students in the sample. So what does that mean? It means that I'm looking in row 11. Why? Because the rows are degrees of freedom, right? So 5 degrees of freedom here, 8 degrees of freedom here, 15 degrees of freedom. And this is only part of the table, right? So there's lots of different rows to look at. But this particular question had 12 students, right? So degrees of freedom is 11. So what's the value we're looking for? 1.796. 1.796. Let me get rid of the highlighting. So what do we do that? Let's call that T star for the moment. Why? Because it's our cutoff value. What did we do? Let me see if I can draw this. Right, so we have this bell shape. And what do? We went in and we drew a line that would do what? That would trap exactly 5% of the area under the curve to the right of the red vertical line we drew, right? That if I draw a red vertical line at T star, I'll trap exactly 5% of the area. That means that any p-value that would be less than 0.05 would be a test statistic value that's to the right of this vertical line. This is the rejection area, the rejection region, right? Out here to the right of this T star value is the rejection region. Those are the places where we're going to reject the null and say we have an evidence for a difference, that these young males have higher aggressive humor scores, right? If we get a test statistic over in this area, right, we're going to fail to reject the null and say, no, there's not evidence that these young males use more aggressive humor than the rest of the population. Okay, so that's what we're trying to do. All right, but we already calculated our test statistic T, right, which was 1.8571. 781, sorry, which is greater than 1.796. Since it's greater, we reject the null. And what does this mean? Our reporting out based on all of this statistical analysis is, because our calculated test statistic T is greater than T star, we reject the null hypothesis, which said what? Which said that the average aggressive humor scores for the young males is equal to 29. Instead, we have evidence for the alternative hypothesis, which said that the aggressive humor scores for young males would be greater than 29. So we have evidence for the alternative hypothesis, right? We conclude that the alternative hypothesis is much more likely to be true. Okay, and we will do a couple more examples in a second. Let's jump over into our notebook and run this. Let's see what's going on. Again, William Seeley Gossett, who worked at the Guinness Brewery in Dublin, Ireland, is the gentleman who created the t-test. And the assumptions of the t-test, you've seen all of this information on the PowerPoint. Okay, here's our hypothesis. Again, that has the same error. And the 0 should be an A, sorry, a lowercase a, sorry, a lowercase a, is the way I tend to write it. So again, the alternative hypothesis is a capital H with a subscript, lowercase a. All right. And what I've done is I've already loaded the data set and subsetted the data frame Y. And you need to know how to do this. So let me go over it, right? I'm using the subset function. The first thing that goes in is the name of the data frame that we're subsetting. And then the next thing is the criteria we're subsetting based upon. So there is a column that's titled sex. So it's column title equals M. This is a character, right? There were two characters, M and F, for male and for biological male, biological female, right? So what we're saying is, hey, subset it, and I only want the rows where in the sex column there's an M. And the ampersand says, hey, there's a second criteria we're subsetting on. Okay, so the OR is a vertical line, kind of like half the absolute value symbol, right? Just a vertical line. That's OR. This is AND. This means this needs to be true, and the age column needs to have a value in it that's 19 or less. And by the way, I could use less than 20, which would work just as well. I could use less than or equal to 19. I put in the less or equal to just so you would see how that symbol works. Okay, what do we do? So we create the subset, which is temp. But remember, subset creates a data frame that's a subset of the original data frame. But temp is still a data set. What am I doing here? I'm using $ notation so that I pull out the aggressive humor scores for just these young males. So I do the subset first to get young males only. And then from the young males only data frame, subsetted data frame, I pull out the aggressive humor scores. So YM is a numeric data vector that has aggressive humor scores in it, only for the individuals we're considering. Okay, data checks. Sorry, the first thing I did is I went into your notes to get the code that does the descriptive statistics, and I've already changed it so that it has the right. Sorry, I have to come up here, download the data, and then now you're seeing how I knew that the mean was 32.25 and the standard deviation 6.06 and sample size was 12, right? Because I'd already done the statistics here in the notebook. So that went into the PowerPoint. Also, we have the 5-number summary. What am I looking at? There's not much to see here. There you go. You might argue if you read the 5-number summary carefully enough that there's a slight skew to the left. Be hard to argue, but I could see that point if you wanted to make it. Okay, so let's look at the graphics that we need to check. Sorry, that's code needs to be marked down. Okay, so I am using the layout and the matrix functions to create a grid. So remember, matrix 1, 2, that just is the slots in the matrix. Number of columns 2. Since there's 2 items in the matrix, that's 1 row, 2 columns. LCM 9, so if you recall in that lecture where I did this, LCM of about 8 tends to work pretty well. You have to see sometimes, so we probably will try values between 5 and 12, but 8, 9 tend to work well. And so here's the density plot density YM, and again, I have a title, box plot YM. I also have a title so we can see what's going on. And now let's look at what the graphics actually produced. So what are we seeing? I mean, I think the easiest thing to see, no outliers. Right? If there were outliers, there'd be a little dot, a little circle down there or up here, right? No outliers in the box plot. Also, now that we're looking at the box plot, you'll see what I was saying, that if you really look carefully at the 5-number summary, you can see that the left tail is longer than the right tail. Not by much, but slightly, okay? Is there skew and outliers? Well, usually if we don't have outliers, we're not really calling it skew. Is there a very slight skew to the left? Yes, there is. You can see it. Oh, and take a look at the density plot. Is this evidence of a bell-shaped data? And again, are we seeing a perfect bell curve? No, we're not. But we're seeing a bell curve like the density plot does look approximately bell-shaped, I think is the way to say it, approximately bell-shaped. There's this weird little anomaly here. For some reason, there were some extra values piling up around aggressive humor scores of 20. I don't know why. But there's nothing suspicious in the density plot. The density plot checks out as well as approximately normal, okay? So that's what we're going to say. We're going to say we have approximately bell-shaped data based on the density plot, and we have no outliers. Perhaps a very slight skew to the left, but the blue text says it all. These data are appropriate for T procedures, right? There's no problem with our data checks. This thing is passed. So let's run the test, okay? And we did it by hand using a table. Let's just let R do the same thing, okay? So t-test, the first thing I tell it is the data. Hey, Remember, YM, that's the young male data vector, right? There's just a vector of numbers here for the aggressive humor scores for young males. Mu equals 29. I have to tell it the null hypothesis. It doesn't know, right? This H sub 0. So we have this mu equals 29. The 29 is the value we would call mu sub 0. It's the population average, okay? And that's what this is asking for. It's like, I don't know what to compare to. If you don't tell me the population, overall population average, I don't know what to compare to. Okay? And so next, alternative equals greater than. Okay, so you can spell out greater. You can spell out less. Or you can just use the first letter. Okay? So let me throw that in. You'll notice that just glance at the values down here, and you'll notice they don't change, right? If I just type in greater. Exact same values, okay? And it just turns out there's a shortcut, and I'll always try to give you the shortcuts when they work, when they're nice and stable. This is just a shorter way to get to where we want to go. It's just saying, hey, the inequality in the alternative hypothesis was a greater than. So I have greater than, I have less than, I have not equal to. All right. And what am I looking at here? I'm looking at the p-value and the test statistic. Remember, we calculated the test statistic. Did we get it exactly right? It matches out to here. It matches out to the thousandth place, but we had a little rounding error. Why? Well, because there's some rounding error in the mean and the standard deviation that we put into the formula. So that rounding error kind of cascaded into a slight disagreement. But there's the p-value. And notice that that R actually tells us what the alternative hypothesis was, that the true mean was greater than 29. Okay, so the true mean for whom? For the young males, young biological males. Okay, and it even gives us the mean for those young males. All right, so now what? Well, now we can do the reporting out. Because the p-value is less than our level of significance of 0.05, we reject the null. And therefore, we have evidence for the alternative hypothesis, which is that the average aggressive humor scores for young males is greater than the overall average for UNG students in Dahlonega. Okay, so the reporting out needs to cover a couple of things. First of all, we want to give some details onto why we're making the decision we made. There's our evidence. Then our statistical conclusion comes in. We reject the null. What does that mean? We have evidence for the alternative hypothesis, which is what? Which is right here. Okay, so you want all three things. You want the evidence or p-value compared to alpha. You want reject the null or fail to reject the null, the statistical conclusion. And third, you want the research conclusion, like what is true after we've taken everything into account. The statistics, the original question, the sample data, what is true. Okay, so jumping back, right? And you'll notice that our t statistic was slightly different when we calculated it by hand. The more accurate value is in R. And we're a little unused to that. We're used to, like in pre-calculus, our calculator rounding and giving us a less accurate value, like square root of 2 over 2 is more accurate. And what is it, 1.717 is the estimate, right? So you say approximately equal to. Well, this is the other way around, where the one that we calculate by hand is less accurate. The one that comes from the machine is more accurate. Okay, so example 2, we've got the variable adult playfulness. And these folks who score high on playfulness, it means that they have some more childlike qualities to their personality. Sometimes you'll see these kind of folks, they'll get down on one knee to talk to a child to be more on their level. They tend to be good at relating to kids. They might splash through a puddle or kick leaves in the fall, or they might sing or dance at odd times. And again, it's not really good or bad. It's just a playfulness, a more childlike quality to their personality. Okay, and so we did this, and we found that the average adult playfulness, the distribution for adult playfulness at UNG Dahlonega was an average score of 127 with a standard deviation of 18. And so now we're going to test at the 0.05 level of significance whether biological females aged 20 and younger have a higher average playfulness score than their counterparts, right, than the rest of UNG. So before it was young biological males, more aggressive humor. Now it's young biological females having more or higher playfulness scores. Okay, we'll see. And we'll run that example in just a second. We have a skyscrapers example. We have a data frame that lists the tallest buildings in the United States. And we're going to check to see whether the average height of the Atlanta skyscrapers in this database are taller than the average height in the database, right? And what's the average height? Well, the distribution for the buildings in the database is 136 meters on average, right? With a 50-meter standard deviation. So the units are in meters. And we're going to test. And now notice that they've given us, we aren't using the standard alpha of 0.05. It says in this case to use an alpha of 0.025, a 2.5% alpha rather than a 5% alpha. Okay, we can do that. Let's jump back into the notebook. Sorry. Let's scroll down to do playfulness. Okay, so notice that I've done a subsetting again. This time the sex is female. Notice that the age is less than or equal to 20, right? It's the same table, so the temporary data frame, remember, the subset creates a data frame from which we have to extract the playfulness scores. So now YF is going to be a data vector with those scores in them, okay? And now what? Well, while we don't really need it or use it that much, we can in fact just do a quick look at the descriptive statistics. So I just went up above and copied this in. And so for young female playfulness, right? And I'll change this to young female playfulness. So we know what we have, and this isn't YM, it's YF. YF. YF, and then that top line, I think, has a YF over there. Let me scroll this way to find it. Yep, there's the YF. Okay, and so now you see that we have the mean, the standard deviation, the sample size of 55. Okay, everything looks reasonable here. Okay, so what am I going to do? I'm going to do the same graphics, and I'm going to grab this Y because it has a nice grid. I like the grid. I don't want to type it all up again. So I'm just going to copy it down here. Sorry, down here. Cha-ching. But now we're pointing at YF. YF. And this is box plot playfulness. And again, notice there's a slightly unequal width there with the LCM of 9, try LCM of 8. And again, you got to play around with this. LCM of 9 might be better. Gives me a little more detail. The box plot I don't need to see that well. First of all, we have a large enough sample size of 55 that we're not really that concerned about a couple minor outliers. There's no outliers at all in the box plot, so the box plot looks great. The question is, is there a bell shape here? Well, okay, remember, what are we looking for? We're looking for evidence that the data were drawn from a bell-shaped distribution. Does that mean it's a perfect bell? No, it's not. Is there evidence to believe a bell shape? Yes. Why? Well, there is, in fact, a tail to the right. It's rather small, but it's emerging. There is, in fact, a tail to the left, which is a little easier to see. Yes, we have a couple little anomalies that, data is piling up a little oddly. But generally speaking, we have evidence of a bell-shaped distribution. So what are we going to say? We're going to say that these data are appropriate, right? Based on the data check, these data are appropriate for T procedures. Using $ notation, the name is LaTeX in math, but a lot of younger computer folks call it $ mathematics, right? DSM. Why? Well, because you enclose the equation in $. And it wasn't an equation, it just sets off the t, so it looks like a variable. And yeah, we've checked out. There's nothing wrong up above, right? We have approximate normality. We have no outliers. Nothing jumped out at us at the descriptives that looked weird. So, and let me open up a few more cells here. What am I going to do? Well, if the data are appropriate for T procedures, let's do one. T.test, young females. What we're going to do is do mu equals, and I don't know what mu is supposed to be. 127. Okay, the average playfulness scores at UNG Dahlonega are 127. So I want a mu equals 127 so that R knows the null hypothesis, and the alternative, I have to tell it, hey, we think that they're going to be higher scores for the young females. Higher score on playfulness means they're more playfulness, right? So whatever attribute we're talking about, if we're talking about perfectionism, a higher score means you are more perfectionistic. A lower score means you're less perfectionistic. If we're talking about narcissism, a higher score means more narcissism. Okay, so this greater than, we're saying that the young females will have higher scores. Okay, and what's going on here? Wow. It switched to scientific notation, right? 1.27 times 10 to the negative 6th. So yeah, we have some real clear, this is really clearly less than 0.05, right? That's what I meant. Why? Well, the average for these young women was 140. Okay, we're testing against an average of 127, right? So this wasn't really a borderline call. The sample data seems to indicate quite clearly that the average wasn't 127. Okay, so what are we going to write here? We're going to say, let's say reporting out. And I am going to switch to Markdown. So my reporting out is what? Well, because, what am I doing? The first thing I'm doing is putting the p-value in, because the p-value, and let's just go 1, 2, 3, 4, 5, 1, 2, 7, 4, because p is less than 0.05, which equals \alpha. In the $ mathematics, \mu \alpha, that's the way we get the Greek letters. Okay? Because p is less than alpha, and am I sure I got this exactly the right number of decimal places? Well, it doesn't matter because it's definitely less than 0.05, and I didn't want to type out the scientific notation. All right, so because the p-value is less than alpha, we reject the null. We have evidence for the alternative, which states that young female students have higher levels of adult playfulness than other UNG students. And again, this is UNG Dahlonega, and the data were collected like in the 2012-2013 era. But yeah, notice that we have the things, right? We have our evidence. We compare p to alpha. We have a statistical conclusion of reject the null, And then we have the what does it mean? The research outcome is that young female students have higher levels of adult playfulness than the other UNG students. Okay. Can we do this by hand? Yes, we could. I'm not going to, but again, we just put these values, put these values into the formula, crank through the formula, and we're golden. Now the skyscrapers, let me get rid of some of this. And I'm sorry, I was working on another example in the airports data set, which is what all that stray work is from. Okay, what's going on here? Well, we have skyscrapers that on average are 136 meters tall in this database for the United States. And we're looking at the average level of these Atlanta skyscrapers. Okay, and this is getting everything. There's only one subset criteria, just to make sure that the city equals Atlanta, right? And now ATL is going to be a list of heights. Let me throw this in. I'm going to switch to Markdown. Why? Because I'm going to do the hypothesis. And I'm going to show you how this goes. Dollar sign, I'm going to do H underscore 0. That gives me an H subscript 0, space colon, and then I'm going to do mu equals what? Equals 136. Okay, and then I'm going to finish with a dollar sign. And now notice what happens. I get the Greek letter mu, I get the subscript 0, right? So that's how the dollar sign mathematics works. And I'm using the Jupyter Hubs onboard formatting. These little leading with a dash space gives me the bullet points, right? I'm going to switch this to alternative hypothesis. I'm going to switch the equal to a greater than, right? And so now I have the hypothesis. I didn't set that up in example 2, sorry. But here's our hypothesis, and we can run the data checks. Sorry, let me get this. Sorry, down here. For skyscrapers. Okay, and now I don't want to do young females anymore. I want to do ATL, right? So I'm sorry, I'm trying to get up to the, damn it. I'm trying to get up to the top here to get the ATL there. Switch from young females to ATL there, switch to ATL there, and ATL there. Cha-ching. So, notice this is for Atlanta. The average Atlanta skyscraper is 150 meters tall, 151, standard deviation of 54.4, and a sample size of 38. Okay, interesting so far, especially when I compare the 150 to the 136. We seem to be in a similar situation as before, but let's not get ahead of ourselves. Let's go get the graphics, right? We're going to do the data checks here. So we need the graphics, and again, these graphics are nice because they have the layout already coded in to do side by side. All right, we're going to do density of the ATL. And that's probably not perfect grammar, but I think you'll understand what I mean when I put ATL skyscrapers in, that it will just help identify exactly what we're looking at. Alt, ATL, not ALT. Sorry about that, guys. ATL, box plot, ATL. And if I get the spelling correct, okay, and we're fine here. right? This does appear to be approximately bell-shaped. This is the problem. Remember, our sample size was 38, if you saw that up there. Just less than 40, and we have an outlier, and what do we do? Well, the criteria that I gave you was if they're outliers and we have 39 data points or fewer, we're not going to run the test. Okay? So, in fact, these data are not appropriate for the t-test procedures. What most people are going to tell you, though, again, that's the most conservative approach, right? The people who use the 35 criteria are going to say, well, you know, it might erode the accuracy a little bit, but it's still going to be pretty valid results. Okay? So let's do this. Let's say what's true, and given what I said, right? Due to an outlier, these data are not appropriate for T procedures. Okay? However, since the outlier is minor and only one exists, we will run the test and be aware of some possible inaccuracy. Right, so I'm going to do this. Why? Well, because I am using the most conservative criteria for 40, requiring at least 40 before we'll start ignoring outliers that are there. This outlier is there. So I'm going to run the t-test, but say, hey, be careful. There may be some erosion of accuracy that goes on. We're going to get a p-value. How accurate is it? Well, it depends on how much that outlier influenced it. All right, so ATL, I want mu equals, and it's 136, right? I got to remember. Yeah, 136. And alternative. We do have other alternatives we'll use. It just so happens that alternative equals greater is the one that we've been using. And now this is interesting. The p-value would have to land right near 0.05. Okay, so what am I going to say? I'm just going to go back up. Right? We said these data are not appropriate for T procedures. There might be some inaccuracy, and we're really, really close to 0.05. Okay. So some people will say, "Oh, fail to reject the null. No evidence that the Atlanta skyscrapers are taller than average." Well, okay, you can say that. Um, or you can say what I said. Hey, the data are not appropriate for t-tests. Again, this is the very problem. I didn't plan on this happening, but this is the very problem we're talking about. What do you do when the p-value is really, really close to alpha? And you've kind of haven't been really conservative about whether or not outliers might affect the accuracy. Well, we know there's an outlier there. We know that outliers do affect the accuracy. The question is, did it affect it enough to cause a problem in this case? We don't know. We may have the right conclusion if we say fail to reject the null, no evidence for a difference in the Atlanta skyscraper height and the height in the rest of the skyscrapers in the table. Okay, but it might not be true, right? Why? Because there is some slight possible inaccuracy. The problem is, even a slight inaccuracy in this case would cause a problem, right? So I'm just going to leave it there. It is a judgment call, okay? And you won't lose points on a statistics test from me for following my instructions, right? um, so data not appropriate, we're not going to do the test, right? But when you do the test, this is the very problem. Some people say, well, it doesn't always turn out that way. What if we had gotten a p-value of 0.02 or a p-value of 0.20? Well, in both of those cases, we wouldn't have been worried that a slight inaccuracy would have caused the wrong conclusion. The problem is that it came out right on, spot on, what we couldn't have happen, right? So this is why statisticians, applied statisticians, data scientists. That's why we have rules. That's why we understand the assumptions. Why? Because R will run any statistics we give it. We are the ones who have to be sure that the data we feed into the procedure is appropriate for it. If we're going to run a t-test, we've got to make sure that the data we're shoving in there is appropriate. Okay? Why? Well, because violating the assumptions of the test, having data that don't comply with the rules, will cause some inaccuracy. How much inaccuracy? It's hard to tell, right? So if we can make sure that we go with the guidelines I gave you, then we're going to be pretty confident of the p-values that are spit out being very accurate. And in this case, you're like, well, who knows? Okay, hope that helps. We will be back to talk about the two other types of t-tests, which are two-sample t-tests. We have an independent samples comparison, and we also have a dependent samples comparison, a matched pairs. This is what we use in pre-test, post-test data, and we'll be back with videos for both of those.